Thank you very much. Good afternoon, everybody. I would like to say thank you for the opportunity to be here today. I find the hydrogen embrittlement community quite exciting. And I am from the nuclear materials community, and we like to destroy materials, but for sure you guys like to destroy much more than us. I recently moved to Leoben. I'm setting up the laboratory for metallurgy in extreme environments. My major focus is space materials. In space, we have the sun, and the sun is constantly emitting hydrogen, proton ions towards the Earth. And this proton impact aluminum case of satellites and spacecrafts, and it causes a little bit of hydrogen embrittlement as well. But the major impact here is when the proton impacts the aluminum, it dissolves the precipitates, and then you have a decrease in the mechanical properties quite significantly. I'm trying to understand if there is a space-related hydrogen embrittlement. Actually, it's very important to be here this year because next year we complete 150 years of hydrogen embrittlement. This effect was discovered by William Johnson, a British metallurgist. He was a bachelor in metallurgy, working in a wire drawing company in UK, and they had wire wires. And after they produced the wires, you had the rust on the surface of the wire, and cosmetically, it's not sellable. And to clean this rust, what they used to do, they used to wash with sulfuric acid. And he reports in these two papers, one Nature paper and the Proceeding of the Royal Society London, that this washing procedure embrittles the iron wire. And if you read the Nature paper, he says if a piece of iron wire that has been cleaned with sulfuric acid be bent rapidly until it's broken, and the fracture surface is moistened with the tongue, they used to do this, licking the fracture surface, they observed bubbles emerging from the fracture surface. He reported this, but he was not the first scientist to study hydrogen effects in materials. It was the French Academy of Sciences, mainly Henri Sinclair de Ville and Louis Catelet. They published all these papers related to hydrogen permeation in metals in this compte rendu. It's available online if you guys are interested. But Johnson was the discoverer of the hydrogen embrittlement effect because he measured the elongation before and after the hydrogen action. So when containing hydrogen, the iron wire had a certain elongation, and then when he expelled the hydrogen by annealing, the elongation increased. So so he measured the mechanical properties. So he was the discoverer. Then the Society of Telegraph Engineers and the Royal Society of London asked Professor David Hughes to validate the results obtained by Johnson. He did this, and he has a paper where he says that hydrogen is the enemy of iron and steel. And we are here 150 years later, and we still not solved the problem. Okay, it's extremely interesting. What we know today has been consolidated in literature by Professor Milos Djukic. We have several different mechanisms, but they are divided into two classes. One is a plasticity-mediated mechanism. Another one is a decohesion-based mechanism. But it may be the case, it almost certainly is the case that they interact with each other. Like, for example, HELP can mediate heat. You have a certain hypothetical critical hydrogen concentration where the two mechanisms happens together. But it's almost sure that at very high hydrogen concentrations, we have had the dominating. The first scientific evidence to support HELP was promoted by the Professor Sofronis and Robertson. I forgot if Utah or Ohio, I don't remember. They had a tensile specimen holder, and they had a gas cell. They put hydrogen atmosphere in the TM with underloading, and they observed that the dislocations move after they release the gas into the TM column. But there is no measurement to a probe to come here in the dislocation and see that there is an increase in hydrogen. In situ experiments, drift can be caused by several other mechanisms that they did not discuss in their paper. They did the same for cracking. They did a crack in an aluminum alloy. And then after the insertion of hydrogen in the chamber under load, they observed that the crack opens, but there was no local measurement of hydrogen. It's a limitation. We have also another plasticity mechanism called HASIV, developed by Ogawa. This is one of the seminal papers in the area of hydrogen embrittlement theory. I highly recommend you guys looking into it. It's actually when you strain the material, you can produce defects, atomic defects like vacancies. They can agglomerate, interact with hydrogen, and nucleate microvoids that the crack procedures happens. There is also the deflectant concept, and I have some new results to present on here. I work a lot with hydrides, transition metal hydrides. I was working with these in Los Alamos National Laboratory. Los Alamos is building a microreactor to generate electricity in the moon in the scope of the Artemis project. We use hydrides because you dissolve hydrogen in the sublattice of yttrium. You form a fluorite structure where the hydrogen is occupying the tetrahedral sites and the yttrium, the octahedral sites. And actually, it's really interesting. The yttrium hydride was the first material enabling the direct visualization of hydrogen atoms. And this was made by Japanese scientists in 2011. There is this paper here from Ishikawa in Nature. After you produce the hydride, you see a lot of dislocations in the structure. Our major objective with this is if a vacancy, if yttrium is displaced in this microreactor due to radiation, the hydrogen vacancy formation energy is reduced. So you have a total vacancy population of hydrogen and yttrium enhanced. So the radiation damage increases in these hydrides, causing disturbance in this hydrogen lattice. We want the hydrogen to be there. Actually, this is a very interesting experiment. This is pure yttrium hydride. When you focus the electron beam in the TM, you can displace the hydrogen, but not the yttrium. So you have a very interesting platform to study hydrogen embrittlement. If you see at the beginning, we have some dislocations, and when the hydrogen is mobile, the dislocations annihilate, and you form a lot of voids. This is 17 minutes of videos in 8 seconds. So when hydrogen is mobile, it does a lot of things, it interacts with these defects in the way that the deflectant concept says for defects. It can also occur, cracking can also occur when you expose the electron beam. If you see here, the crack initiation and some surface cracking. It's actually quite interesting, the idea of using hydrides, because they dissolve quite a lot of hydrogen. We have the decohesion-based mechanisms, and the idea here was developed first by Pfeil a couple of years later after Johnson's discovery. It has been developed by Troiano, and the major idea is when hydrogen enters into the material, because of Coulomb interaction, you have repulsion, and this repulsion causes decohesion or the elimination of planes or destruction of bonds. With hydrides, we observe a very interesting phenomenon supporting head, in my opinion. You have a zircaloy in nuclear industry, which is zirconium 1.5 tin alloy. The tin is fully dissolved substitutionally in the zirconium lattice. When you hydride to form the hydride pellet, all the tin goes out of solid solution. So the hydrogen enters in this tetrahedral sites in the solid sublattice and expel all the solid solute atoms. It's quite interesting. The limitation of hydrogen detection in material sciences is here. We have only one technique that is capable to detect hydrogen at sub-nanometer scale, which I call nanoatomic scale, and it's APT. And if you go to the literature to see what people do with APT, they actually do not measure directly hydrogen, they measure deuterium, because hydrogen contamination, it's quite significant for these guys. And they basically measure the trapping ability of some precipitates. But this is known experimentally since 1980s. If you go to the seminal review from Myers, which is a researcher in Sandia National Laboratories, they measured this with SIMS. So we know that carbides have a huge ability to bind with hydrogen. In Leoben, we have 2 future projects where we are going to address the limitations of hydrogen detection. One, unfortunately, Hydroingenious. It's under the conceptualization stage again. Professor Milos is our collaborator. We will develop a new technique to directly quantify and measure hydrogen at the atomic scale. This is based on plasmon emissions. We have other project that I'm going to talk about here today. It's called Hydroinvision. We are going to study the phenomenon of hydrogen in action. When we put hydrogen in the material, what happens? How the hydrogen metal interactions takes place. So this technique is using the shifts of the local electric field in the material when the electron beam in the TM passes through it. It's using classical Maxwell theories. And this is some results I'm going to show with a paint-baked crossover alloy, aluminum magnesium silicon with 2% strain. It's an alloy that is hardened with the T phase. This technique, if you pass an electron beam through a specimen, you generate electric fields, and these electric fields are dependent on the microcircular sites. And you can measure the momentum of the electron beam. This is the alloy viewed with dark field. You can see we have precipitates, dispersoids, and a lot of dislocations because it's 2% plastically deformed. And this is the DPC image. What you are seeing here, it's the electric field components, X and Y, in this specimen at the local sites. Okay, just to show you guys the potential of this technique to study hydrogen enrichment, I did another experiment, a high magnification with a different alloy. It's a pre-aged alloy. And in the pre-aged condition, instead of having precipitates, we have GP zones, much smaller. With the TEM, we can barely see them. You can barely see them with EDX. Only with APT, you can resolve them very well. And unfortunately, we cannot see very well, but we have here dislocations, the matrix, and these green guys here are the precipitates. And this is just the shift of the electron beam. And what we can do with this, we can do image segmentation. This is the aluminum alloy matrix. The contrast is not very good, but we can separate the GP zones and the dislocations. Maybe I can go back. You see, this is the electric field image. Then I have the aluminum alloy matrix. So imagine that if we charge here hydrogen, we monitor what happens with the signal of the electric field in the sample. And this is one of the ideas we have.
2 minutes.
Yeah. This is the dislocation. And you can see that the dislocation has also a halo here, which I call the zone of dislocation influence. Is not directly the strength field. So this project, we are going to develop the Leobner hydro gun. This is going to be a TM holder that we will implant hydrogen at very low energies, 0.5 kV. And the concept, we demonstrated the concept with helium. This is a high entropy alloy. You are seeing directly helium implantation. I created the indent here with a fib. So when we implant hydrogen, what you see at the beginning is the formation of dislocations. See, and then there is transient where the dislocations accumulate, but this concentrates stress, and we have a crack forming. We will also study in this project the relationship between the hydrogen and the dislocation using quantum mechanics, because nowadays, very recently has been discovered that we can use quantum field theory to model dislocations. Dislocation is a quantized quantum field. It's basically lattice strain plus vibration. And we wanted to measure with DPC how hydrogen changes both the strain and the vibration in the lattice. We can do this with the electron beam vector. We are looking for collaborators to join our projects. And we are highly focused in experimental science. And if you guys are interested, I'm mostly welcome to collaborate with your community. Thank you.